equals to 0, then result as n equals to 0. Okay, so if p dot 1 n equals to 0, or p2 dot n equals to 0, then product dot n equals to 0, return no. Yeah, actually, return prod. We're not going to initialize the coefficient array if n is equal to 0. It means there's no coefficient array, basically. One of these terms was equal to 0. So polyprod, that. Okay, otherwise prod.n equals p1.n plus p2.n. You have to minus 1 because n is 1 more than the degree. So if you want n for this, it's 1 more than the degree, but here you add 1 twice, so you need to only add it once, and that's why you have to subtract by 1. And then one way to think about what's happening is you can think of distributing by saying this A will multiply E and F, and it's going to go here and here. This B will multiply E and F, and it's going to go here and here. C is going to multiply E and F, and it's going to go here and here. So int I j for I equals to 0, I smaller than p1.n, I plus plus. You're going to visit all the coefficients here, and then you're going to visit all of the coefficients in the other array. And then prod dot coefs. Oh, we need to allocate. So if we have B which is I equals to 1, and we multiply by f, which is I equals to 1, we're going to go in the second slot, or the slot equals to 2. So if you try a few more, you're going to see that it's taking this, multiplying by that, I, j goes in the I plus j position. I plus j. Plus equals. Plus equals p1 dot coefs I times p2 dot coefs j. That's the simplest way of doing that, but you have to do this thing for I equals 0, I smaller than prod at n, I plus plus. Before you do any of that, you've got to put everything to 0. Initialize, because otherwise when you try to add to this position, you're going to get into trouble. So this way of looking at it, you loop over the first array, the second array, then you combine the result. And the looping is over this and that. You could also loop over the result and then go find whatever you needed to find. So for example, for this thing, this position, you would just need E and A. For the second position, you would need E and B and A with F. For the third, you would need E with C and F with B, and so on. So you could do that as well. So maybe, I don't know if this is appropriate at this time to mention this, but if you had to compute this in parallel, it would be better to loop over the results and have basically one worker assigned to each result, or maybe to multiple results, but the point is that no two workers would try to write at the same place. So you could you wouldn't have any kind of bad interactions like that, but it would be possible for different workers to read from various places which are the same. You know, it would be possible for worker 1 to read C while worker 2 reads C as well. That's much easier to deal with. But unless you're multiplying pretty big polynomials, this is like instantaneous, you know? This is, yeah, it's pretty fast. if you wanted to make it faster, and you were starting to worry about you know, having parallel workers, probably something to look at first is, instead of using the standard allocator, to use an allocator which is more specialized for this kind of draft kind of pattern of usage. You might think of a use case for this where you create a big polynomial by multiplying, and then you subtract two such big polynomials, and you get a small polynomial that way, and you can clean up and only have a few going to just do exactly what I figured out that needed to happen, but first we have to return. Let's multiply poly with itself. So you get 49, which is 7 times 7 plus 84 x to the 1 plus 106 x to the 2 plus 60 x to the 3 plus 25 x to the 4. To make sure we're doing everything correctly, let's do some binomial polynomial. What is this going to do? As you can see, this basically does Pascal's triangle. So 1 plus x, when you square it, it's x squared plus 2x plus 1. When you put it to the 4th power, it's going to get 1, 4, 6, 4, 1. 1, 8, 28, 56, 70, 56, 28, 8, 1. Right, so you get you can look that up. Maybe you can look at Pascal's triangle. Pascal